We have developed soft electrode array that can be deployed below the skull at the surface of the brain. This is useful to enable measurement of neuronal activity in the context, for example, of epilepsy. When they're fully deployed, the electrode array look like a flower with multiple spiral petals. They are about 4 centimeters in diameter and they're very thin. They're about a few hundreds of microns in thickness to fit the very narrow space between the skull and the brain. This is to answer a specific request from neurosurgeons who are hoping to have minimally invasive devices so they can have, through a small hole in the skull, a large area coverage of the surface of the brain. Our very first prototype was really like a flower with straight legs, straight petals. And when we made this device, we realized there was a lot of open space remaining at the surface of the brain. And therefore, we decided to engineer curvature into the arms of the flower, of the petal, so that we could have a larger surface coverage. So we had to come up with a deployment system that would be gentle enough not to compress or damage the underlying brain, and strong enough to sustain the deployment in this narrow space. So we got inspiration from soft robotics, and we used a mechanism that is called eversion, which is flipping inside out the device.
So the beauty of eversion mechanism is that we can deploy an arbitrary size of neural electrode with a constant and minimal compression on the brain. This eversion mechanism can emulate the motion of growth of the tree roots. And there's no limitations in terms of how much the tree roots can grow.
So if you consider that our soft electrode array is like a glove and each of the fingers correspond to one of the arm of our electrode array, we have electrodes that have been manufactured on each of the inner side of the array. And then we first fold the electrode array just like you would fold your glove inside out. And then using a pressurized liquid, we can then apply a gentle pressure to help deploy right side out each of the fingers at the surface of the brain. We had to come up with material that would sustain the enormous mechanical deformation that is required to deploy the devices. So we use materials that are very compliant, like elastomers, like a rubber band type of material, and a technology we have developed in the lab to produce stretchable thin metal gold. So we think this is a technology that could be deployed widely at the clinic because of its minimally invasive nature. So now what we hope to achieve is to scale the technology to fit it to humans and increase the number of electrodes so that we can have richer information from the brain.